Surfing powerful ocean waves like these takes tremendous skill and strength. Paddling through waves is also a difficult thing to do. What forces create these waves? Why are waves bigger some days than others? And what gives waves such tremendous power? The waves generated by earthquakes are powerful enough in some instances to topple large buildings like this one. And waves generated by explosive devices like these have enough power to blow apart huge slabs of rock. During the next few minutes, we're going to explore some of the different types of waves, while also taking a look at the characteristics of waves and how we use waves in our everyday lives. Notice how this grass blowing in the wind creates wave-like patterns. And notice how the waves pound the shore on this stormy day. What is a wave? A wave is a disturbance that carries energy through matter. A wave does not necessarily move the matter or medium, but instead flows through or creates a disturbance in it. Take a look at this ball as the motorboat creates a wave. Notice that the ball does not move forward with the wave, but merely moves up and down as the wave moves under it. This demonstrates how a wave carries energy from one place to another through a medium. This can also be illustrated by watching this rope tied to a post. When we shake the rope, notice how it creates a wave-like pattern, transferring energy from one end of the rope to the other. You decide. What force creates these waves? That's right, wind. If you've ever been to the beach on a windy day, you may have noticed that the waves tend to be bigger than on a calm day. That's because the wind is transferring its energy to the water, causing it to move. You've also probably created waves yourself by kicking your feet in the water. Energy, often in the form of vibration, is necessary to produce waves. For example, when this guitar string is plucked, it vibrates back and forth quite quickly. The resulting vibration creates sound waves, which are waves that we can hear as music. Perhaps in the movies, you've seen someone put his ear on a train track to listen for a distant oncoming train. Why? The sound waves from the train travel more quickly through solid materials, such as the train tracks, than they do through the air. Therefore, you can hear the train through the metal tracks before you can hear it through the air. The substance or matter through which a wave travels is called a medium. Ocean waves use water as a medium, but water can also serve as a medium for sound waves. For example, whales can hear each other for miles through the water. Mechanical waves require a medium through which to travel, and sound is a type of mechanical wave. There are also waves that do not need a medium through which to travel. These are called electromagnetic waves. You decide. Can a mechanical wave, such as sound, travel in the vacuum of space? No, mechanical waves, such as sound, require a medium or matter to travel through. In space, there is little or no medium through which to travel. However, light, such as that from our sun, is an example of an electromagnetic wave that has the ability to travel through the vacuum of space. While there are many different types of waves, all waves have the following characteristics: amplitude, wavelength, and frequency. By studying these parts of waves, we can see what makes different kinds of waves unique. You've probably heard the term wavelength before. It's the distance between a point on one wave and an identical point on the next wave. If you measured the distance between the crest of this wave and the crest on the next wave, you would find the wavelength. Wavelength is usually measured in meters or centimeters. The amount of time it takes for a wave to travel the distance of one wavelength is called the period. You can find the period of the wave by calculating the time it takes for a wave's crest and the crest of the next wave to pass by a point. Frequency is the number of complete waves per unit of time. You can think of frequency as the number of crests that pass a point per second. Frequency is measured in a unit called hertz. 1 hertz is equivalent to 1 wave per second, and it's symbolized by the letters Hz. The numbers on an FM radio dial are in units of megahertz, symbolized by the term MHz. It's easiest to visualize waves by drawing them on a graph. This horizontal line represents the x-axis, and this vertical line represents the y-axis. This is a wave with a regular pattern. This wave pattern illustrates the rhythmic sound of crickets, which produce this sound by rubbing their legs together. This distance from the x-axis to the top of the wave is called amplitude. Amplitude is a measure of the amount of energy carried by a wave. This wave pattern illustrates the sound made by little frogs called peepers. This sound is louder than the crickets and therefore has greater or higher amplitude. You decide. What do the X-rays that created this image of a hand, the microwaves used to cook this food, and radio waves all have in common? These waves are all electromagnetic waves, which are a type of transverse wave. We'll use this rope to illustrate how transverse waves work. Notice that when one end of the rope is shaken, a moving wave forms and the energy is transferred along the rope. While a given piece of the rope moves up and down, the wave moves horizontally. It can be said that the movements are perpendicular or at right angles to each other. This is the defining characteristic of transverse waves. The direction of a transverse wave is at a right angle to the direction the wave travels. Earthquakes are produced when the plates of rocks beneath the surface of the earth move, releasing built-up energy. This energy is transferred throughout the earth in the form of seismic waves. This slinky is a common toy that easily illustrates longitudinal waves. Watch the slinky closely as one end is pushed. Notice how the wave doesn't move up and down, but instead moves horizontally. This diagram describes the action of longitudinal waves in more detail. As the wave moves from left to right, particles collide. This forms an area where particles compress. This collision of particles is called compression. When the particles separate, this is called rarefaction. While the particles compress and separate, the wave moves forward. Sound waves are a type of longitudinal wave. Some sound waves can be extremely powerful, such as those produced by airplanes, or explosions from a firecracker, or in special hammers that are powered by cartridges of gunpowder. All these examples utilize longitudinal waves. You decide. Why do you hear the clap of thunder after you see the bolt of lightning? Even though the bolt of lightning and the clap of thunder are produced at nearly the same time, their waves travel at different speeds. The electromagnetic waves of light from the bolt travel more quickly than the mechanical sound waves of the thunder, causing the flash of light to reach your eyes before the sound reaches your ears. Wave speed varies with the type of waves and with the medium through which waves travel. It's possible to calculate the speed of a wave if we know its frequency and wavelength. Wave speed equals frequency times wavelength. There are four main ways that waves interact with other mediums. These are reflection, refraction, diffraction, and interference. You decide. What happens when you yell across this valley? If you said that you hear an echo, then you're correct. An echo occurs when sound waves bounce back off an object, like these mountains. This process is called reflection. Reflection is the bouncing back of a wave after it strikes something that does not absorb all of the wave's energy. The incoming wave is called an incident wave. The wave that bounces back is called a reflected wave. Reflection also occurs when you look in a mirror, or when you see the reflection of objects in water. Waves usually travel in a straight line. But what happens when waves pass at an angle from one medium to another? As you can see, the wave bends. When the light wave moves from the air to the water, the wave slows down, causing it to bend. The bending of waves due to a change in speed is called refraction. As waves pass at an angle from one medium to another, such as light entering and exiting this diamond, they may speed up or slow down. The speeding up or slowing down of light is what causes refraction. Waves can also bend around the edge of an object. You decide. What enables you to hear the horn from this car on the other side of this brick building? The answer is diffraction. For example, when you stand in water and you look down at the waves, you notice that some small waves are reflected. But when you look behind your legs, notice how the waves have reformed. This is an example of diffraction. Sometimes two waves meet and combine to form one wave. This is called interference. Constructive interference happens when the crest of one wave meets the crest of the other wave. Destructive interference occurs when two waves combine in such a way that the new wave is smaller than either of the original waves. Waves are part of our everyday lives. They allow us to surf on the ocean. They also allow us to hear other people talking and to sense our environment. During the past few minutes, we've examined some of the basic characteristics of waves, beginning with the nature of waves. We studied how waves carry energy from one place to another by flowing through a medium. And we took a look at different types of waves, including transverse waves and longitudinal waves. We took a look at the different parts typical of a wave, including wavelength, frequency, and amplitude, and how waves interact with matter and each other. So, the next time you go to the beach or hear a sound, think about some of the concepts of waves. You just might look at waves a little differently. Fill in the correct word when you hear this tone. Good luck, and let's get started. Number 1, is a disturbance that carries energy through a material or medium. Number 2, is necessary to produce waves. Number 3, the substance or matter through which a wave travels is called a Number 4, is the distance in a wave from the medium to the crest or trough. Number 5, is the distance between the crest and the trough of a wave. Number 6, is the number of complete waves per unit of time. Number 7, a wave is always at a right angle to the direction of the wave. Number 8, is the bouncing back of a wave after it strikes a boundary. Number 9, is the bending of light due to a change in speed. And number 10, when two waves meet and combine to form one wave, it's called